All right, today is Tuesday, November the 10th. We are in AP Chemistry with Spain Park High School. And if you're enjoying these daily videos, please feel free to subscribe to my channel and like this video. I am going for 100 subscribers. All right. So yesterday, at the end of class, all I count from here. I love y'all. I love you too. You never know the surprises. That's why Uzma was checking on me.
Yeah.
Is he coming yet? Is he coming?
I was gonna add a dash Senor Hobbs. Just.
Okay. So we began talking, and this is still left here from yesterday. Okay. So we were talking about the properties of covalent substances. We only got to covalent network. Okay? So we need today to talk about covalent molecular. And we know how to recognize covalent molecular because it's going to be what?
A molecule.
Yeah, but of what type of elements? Two nonmetals, okay? Whereas an ionic is going to be a metal and a nonmetal. So we can just kind of look at covalent molecular. Now we have two types of covalent molecular, polar and nonpolar. So if we look at nonpolar molecules, okay? What's the only type of IMF? LDFs only. Contain only weak LDFs. So what does that mean about the melting and boiling points?
Low.
Very low melting and boiling points. Meaning they're going to be what state at room temperature? Gases or most are gases or volatile liquids. What does the word volatile mean in this sense?
It could change shapes.
No, that's malleable. I heard somebody say in the back. It evaporates quickly. Okay? It evaporates quickly. And if something evaporates quickly, what does that mean about its vapor pressure? You have notes. Yeah. Okay, the vapor pressure is going to be high because if it evaporates quickly, you have a lot of vapor, and as a result, you're going to have a lot of vapor collisions with the container wall, and you have a high vapor pressure. Okay? So we can just kind of say a high vapor pressure. Okay? So what do LDFs, what determines the strength of the LDF? The size of the electron cloud, right? And so as a result, okay, just remembered something. As a result, as you increase the size of the molecule, you're going to go from gases to liquids. So if we look at CH4, C2H6, C3H8, C4H10, H10, C5H12, C6H14, C7H8, pardon me, 16, C8H18, and we could just kind of go on and on. These first four are all gases at room temperature. This is methane that comes out. That's the natural gas that comes out of here. Ethane is kind of a mixture. There's a little bit of ethane in here as well. They're gases. This is propane. This is what's in the white, tank for your barbecue pit outside. Okay, it's going to be propane. Butane is what's in a lighter. Like even the striker is going to have butane in it. It's under pressure, and so it's a liquid. You can see the liquid inside it, so it's getting bigger, so it's easier to compress into a liquid. But as soon as you take the pressure off, in other words, you squeeze it, the liquid just changes into a gas, and that's what it's actually burning when then you have a little striker that makes a spark that lights it. But it's a gas that's burning. It's changing here. But these are all volatile liquids. Okay, volatile liquids. So as you get heavier and heavier, now you get up into 18, 19, 20 carbons, then you're going to get a paraffin wax, like a candle wax. Still going to be a solid, but still going to have a pretty low melt. They melt easily, low melting and boiling points. But again, the bigger the molecule, the stronger the LDF, the higher the boiling point. What about polar molecules? What do they have? They have LDFs, dipole, and possibly hydrogen bonds. I don't like the word contain. IMFs, LDFs, dipole. And possibly H bond. So what does that mean about the boiling points compared to nonpolar? Generally higher. Now, if you're comparing a small polar molecule to a large nonpolar, the LDFs might be stronger than the combined dipole, and LDFs here. Okay, so you have to look at the boiling point is going to be the ultimate determiner. Whichever one has the highest boiling point is going to be the one with the strongest IMFs. Okay, but generally, higher melting and boiling points than nonpolar molecule. Still mainly gases and liquids. At room temperature. Now, for both polar and nonpolar, what do we think about conductivity, the electrical conductivity?
Good.
What is conduction of electricity? What is
Flow of charged particles.
flow of charged particles? Are these going to conduct?
Which one's polar?
Or either one? Is polar considered a charged particle?
No.
What's the definition? What word is a charged particle? An ion. Okay? Molecules are neutral. They have a positive and negative end, but they're still neutral. If they're neutral, they're going to conduct electricity. Anyone? No, because electricity is the flow of charged particles. So, neither conduct electricity okay, neither conduct electricity because they are composed of neutral molecules about it? Are they gonna be malleable? Is an ice cube malleable? No, you hit it, it's gonna shatter, right? You drop it, it shatters, okay? So these things are brittle. Okay, this isn't just polar, this is all. Okay? So they're neither malleable or ductile, they don't conduct electricity, they're gonna have relatively low melting and boiling points, and as a result, they're gonna still be a gas, but depending upon whether they're polar or non-polar, it's gonna make the boiling points vary. Water is a small molecule. If it weren't so polar, if it didn't have the hydrogen bonds, it would definitely be a gas at room temperature. But because of the strong dipole and hydrogen bonds in it, it ends up being a liquid at room temperature, but it still boils at 100 degrees, whereas ionic and metallic substances in covalent network boil at 6, 7, 800 or higher degrees. Okay? So we can now look at all of the different characteristics. So this chart that I'm about to give to you summarizes everything we just talked about. This is the chapter in a nutshell. How come I don't have two? I'll find one for you in a second. Okay, let's see. Probably molecular geometry. I have one in my file, I'll get it to you in a second. Okay. Go ahead and bring it off the top. So if we look over this, we can just see the smallest part, that ionic compounds are composed of ions. Metallic compounds are metallic elements are made up of just single one type of atom, the simplest of all crystals. Covalent network, how are we going to know it's covalent network? It's got to be one of these five. That's how we're going to know. It's one of these five. It's going to be covalent network, and then we have a covalent molecular. So we need to be able to describe the characteristics and properties of the things based upon that. And we're going to spend a lot of time today kind of doing some practice problems with that. But before we get to that, I just want to share one other thing with you. A point of interest, an application of chemistry in real life, dealing with molecular geometry. What's the difference between a fat and an oil? Okay, you're on the right. I heard somebody in the back. Saturated and unsaturated. Okay, a fat is saturated, and we're going to talk about what that means. An oil is unsaturated. What state? Unsaturated. Okay? That should have the U. What state? When you think of a fat, what state do you think it's going to be?
Solid.
Solid. Whereas an oil is a liquid. They're both going to be long hydrocarbon chains, 16, 18, 20 carbons in a chain long. It's just going to be the type of bonding. And so, Jaden, you obviously, maybe from AP biology, remembering saturated, unsaturated. What does it mean to be saturated?
It has a, it's not thin, and so
It is going to be more linear. But what does the term saturated, that's the shape of it, okay, and we're going to get into that. But what does it mean to be saturated?
Does that mean there's a hydrogen around
there's a hydrogen around. In other words, it's saturated with hydrogens. You can't add any more. Yesterday we talked about partially hydrogenated vegetable oil, I think. Maybe I did or I didn't, okay? But you can break double and triple bonds by adding hydrogen, but once it gets to all single bonds, you can't add any more hydrogens. It's saturated with hydrogens, okay? So it contains all single bonds. So therefore, if it's unsaturated, what is it going to contain?
Double.
Okay? Contains double or triple bonds. So sometimes you'll see polyunsaturated vegetable oil. What would polyunsaturated mean? It has multiple double and triple bonds, not just one in the chain. Okay? So there's going to be a lot of places for it. Now, here's the deal. This is what Jaden was kind of alluding to. This is the start of a long hydrocarbon chain. This is all single bonds. And even though it's zigzagged, it's still fairly linear. As you go across, as you get it, it's still going to be pretty much in a line. The London dispersion forces have a whole lot more surface area here, and so you get stronger London forces. So the long chains tend to stack on top of one another, and they collect in your arteries, and increase your cholesterol and clog your arteries. Now, unfortunately, saturated fats taste better than unsaturated fats. Saturated fats have a higher boiling point because they have the stronger London forces. So as a result, you can cook your fried chicken at a higher temperature so it cooks more quickly, and it's crispy on the outside and not greasy on the inside. And it's got a longer shelf life. It stays without spoiling longer. But it's not good for you. It's increases your chance of having a heart attack or a stroke.
So like if we completely boiled ourselves, the fat would be gone from us?
If you boiled, well, the fat's it is eventually gonna melt, but it's not gonna necessarily decompose.
That's what I'm using.
So, I don't think there's a way to melt away the fat. On the other hand, if we have something that's polyunsaturated, okay, I have a double bond here, a double bond here, and a double bond here, you can see that it's much more bent. It's much kinkier, okay, in that it's got all these bends in it. So it makes it much more difficult for it to stack. The London forces are weaker, so it can be a liquid at room temperature, not a solid. So if we partially hydrogenate this, that means we're going to add some hydrogens to it to break the double bonds, but we're not going to break them all. We're only going to break some of them. And the more you break them, the more it straightens out the chain. So there's the compromise. This is more healthy, or we should say less bad for you, than this one. This one tastes better. So they kind of try to change this one into kind of halfway, medium, partially hydrogenated, so they kind of keep it somewhat unsaturated, but yet, we want to try and make it taste good. So there's a balance in there. Now, the thing is, have you all ever heard of the term a trans fat? Mm-hmm. What is that?
It's being transformed from
It's being transformed. No. And the dot, dot, dots implying that the carbon chain can continue on. Notice here, in this molecule, around the single bonds, you can rotate. Things move around in a single bond. But in the double bond limits the rotation. You can't spin it around. It's much stiffer. So we have, on this one, the chain continues on the same side of the double bond. This one's both on top. If you flipped it over, they'd both, be on the bottom. We call this the cis isomer. Okay? But we could also have it come across. And when it goes across the double bond, one on top, then it extends on the bottom, across like the Transcontinental Railroad went across the continent, this is called the trans isomer. Isomer is same exact formula, just different arrangement. It's a geometric isomer. Okay? So this is pretty much going to be your fats. These are going to be your oils. These are bent. When you go with this, if I go, notice here I have them both coming off the same side. If I change these around and change it to the trans, okay, do the same thing off of this one. And then do the same thing off of this one. So I'm going from the cis isomers into the trans isomers. Now, look at the shape. Much more linear again. So it turns out that a trans unsaturated, polyunsaturated, can still be linear. It can still have the same negative characteristics as a saturated fat. So in, my lifetime, well actually a little bit before that, in the 40s and the 50s, they started getting medicine and starting to, heart attacks, understanding what's causing heart attacks and that kind of thing. And they said, ooh, these saturated fats are building up in the body. So they said, we need to make polyunsaturated. So they made margarine. But then they started looking more carefully and techniques of being able to see the molecular structure improved. And they found out that when you're in the making of margarine, it was forming these trans fats that were just as bad. So then they came out in the 80s and 90s and said, well, you ought to just go ahead and eat butter because at least it's natural. And so it's just kind of back and forth. But now you see everything trans fats, zero trans fats, because now they're trying to make it all. So if they just talk about polyunsaturated fats on a food label, they're talking about the cis formation. They don't call it cis fats. They just say no trans fats, because this is the bad one. People don't understand the difference between the two because they haven't taken this class. But now the rest of the world knows. Just watch the video. Why you should subscribe. You learn all this great stuff. Okay? But that's what, when you see trans fats, that's kind of what we're talking about. It's just the isomer that goes across the double bond causes it to be more linear. But in terms of fats, it's much better to be kinky. And so, you're allowed to smile on that, okay? But I said it only in terms of these molecules. Okay. So, we need to just now practice. We need to practice. So we're going to look at one of my all-time favorite questions.
Goodness.
Always takes so long to warm up. Okay, so this is a picture, pretty much of this thing right here. Okay, you got the light bulb, you have the two exposed wires, okay, and you're sticking the sample in a beaker, and then kind of putting it, the two wires into that beaker. Okay, if the solution conducts electricity, the light bulb comes on. If it doesn't, then it doesn't come on. We've seen that with electrolytes and not electrolytes. So that's what this is. So now we're given 4 substances: silver nitrate, sucrose. What sucrose common name is? Sugar. Does anybody know the formula of sucrose? That's glucose. Put 2 of them together.
C12H24O12.
Well, but they come, well, you're close, but when the 2 monosaccharides come together to form a disaccharide, it uses a condensation polymerization. Okay? Hydration synthesis maybe is what it got called. So that means a water gets formed, and OH comes from one of them and H comes from the other one, makes a water, then the 2 can bond together. So sucrose is C12H22O11. Okay, so there's minus, so it's the 2 put together minus the water. All right, that's neither here nor there. But what does that make it? What type of compound does that make it? Ionic, metallic, covalent network, covalent molecular. Covalent molecular. Then you have sodium and you have H2SO4. And well, what's the name of H2SO4? Sulfuric acid. Strong or weak?
Strong.
How do we know that?
The charge.
The chart, we memorized it, right? Then we know the top 6. We know the 6 strong acids. So, it talks about the electrical conductivity. So what does it mean if it says fused? That's a fancy way of saying melted. Okay? Dissolved in water in aqueous solution, or the solid. 2 pluses means it's a good conductor. A plus means that it's a poor conductor, but still a conductor. And a minus means it's a non-conductor completely. So, explain the difference in electrical conductivity using chemical bonding and atomic or molecular structure. Why is sucrose solution a non-conductor, whereas a silver nitrate solution is a very good conductor?
Do I have to write it?
No, I want just think about it first, okay? Who wants to answer that? Somebody that had an answer, who doesn't know the answer. Come on, people. You know the answer. You know the answer. What do you think, Anthony?
I don't know, I'm still figuring it out.
Okay?
Maybe
Well,
because,
go ahead.
silver nitrate is an ionic
Compound.
compound, so it will be, once it's dissolved in the water, it dissociates, so we'll be able to, the Ag plus ions and the NO3 minus ions will be able to flow.
That's right.
And
Okay.
the
Sucrose.
is covalent.
Covalent network, covalent molecular.
Covalent molecular.
Okay, so let's just say this, okay?
It's a covalent molecular, so it can.
How does it dissolve?
It ionizes.
Does it ionize? It dissolves with molecules, right? Neutral molecules. What's the definition of electricity? The flow of charged particles. So will there be any charged particles in a sugar solution? No. Okay? So, as Hampton said, when silver nitrate dissolves in water, since it's an ionic compound, it's going to dissociate into the ions, so you'll have ions that have freedom to flow, conduct electricity. Okay, they're not going to produce the electricity, they're just going to allow the charge to flow through it. Whereas sucrose, is going to dissolve as neutral molecules, which does not allow for the flow of charged particles. Okay? Now, solid silver nitrate is a non-conductor, but solid sodium metal is. Okay? Ionic, okay. Sodium and ionic solid, well, let's just do this one. Do we have charged particles?
No.
Well,
But they're stuck together, right? They're held in a rigid crystal structure, so can they flow?
No.
Okay? So you would say, silver nitrate, solid silver nitrate is an ionic compound, and the ions but the ions are held rigidly in place and cannot flow, so it doesn't conduct. Why does sodium conduct?
Because it's a sea of electrons.
Say that, Paris, what?
Because it's a sea of electrons even in its solid.
Okay, what type of bond is that though?
It's a metallic.
It's a metallic bond with the sea of free-floating valence electrons. As a result, you have charged particles that can float. It conducts electricity.
Did you say the electrons become delocalized?
Sure. But again, I always like the definition that electricity is the flow, but the electrons become delocalized and can move, which is electricity. Okay? Now, fused sucrose is a non-conductor, but fused silver nitrate is a conductor. Melted. When sugar melts, what happens? Go ahead.
So, when sugar melts, it's just a bunch of neutrally charged molecules just all around, so an electric current applied. There's no charged particles.
Okay? Whereas when silver nitrate melts,
The rigid crystal structure breaks down, and there's just a bunch of charged particles floating around.
so the ions kind of break apart from one another. I don't know if you would use the word dissociate. I think that's really only in water. I'm not sure. But the ions break apart and get mobility. Right? So these are all the properties. I like this because it's just making you know the properties of the four substances. And then lastly, concentrated, this one's a little more tricky. Concentrated sulfuric acid is a poor conductor, but still a conductor, and that's 98% pure. It's almost all H2SO4, only 2% water. But the more water you put into it, the better conductor it becomes. What is the water, if it's a poor conductor, what does that mean? It doesn't dissociate or ionize completely. Okay? What does that mean about the number of ions present? There's small amount, not very many, but there are some present because it conducts, but not many. So when you only have 2% water, you've only pulled a few of the hydrogens off. But as you add more and more water to an acid, and again, what type of acid is this?
Strong.
So what does that mean about its ionization? Is it partially or completely ionized?
As you add water,
As you add water, it completely ionizes, right? And so that causes it to have a whole bunch of ions then, and it's a much better conductor. Okay? So, now that we've talked about all that, now I do want you to write these answers down. See what you can do from memory. See what you can do from memory. Okay?